Hello everybody. Let us start today's class regarding the continuum plasticity. So last class what we have discussed, that was only focused on the one-dimensional uh, stress or strain relation, specifically when you do different type of test, for example tensile test, torsion test. So we also discussed that the effect of the strain rate, strain hardening effect, yielding, all these phenomena in terms of one-dimensional stress state, or maybe in case of mostly for tensile testing. And now today we will try to discuss the continuum plastic behavior of the materials in actual case. For example, if practically when the state of stress in three-dimensional, then in this case how we can evaluate the different plasticity model to represent the actual cases. We discussed that flow, yield and fracture criteria actually represented in terms of the stress in such a way that it is valid for all state of stress. So of course here the unidirectional state of the stress also equally important here, and that will try to correlate in some equivalent form with respect to the three-dimensional state of the stress or strain. Second point is that a material can be considered failure either by yielding or fracture depending on its properties and the state of the stress applied to the specific material. So the criteria is to set that predict the failure by yielding and others failure mechanism, but here focus is only on the plastic deformation of the material, not the different failure criteria. So yield criteria specifically applies to a material that is in annealed condition, specifically for the ductile material, and the failure criteria applies actually both ductile and the brittle materials. However, failure criteria is mainly focused on the brittle materials in which the elastic limit of the deformation actually decides the failure criteria, specifically in case of brittle material. But flow criteria applies to the materials that have been previously processed via work hardening mechanism, and that is specifically ductile materials. So along with the yielding criteria and the flow of the material basically is the main focus of continuum plasticity, and specifically in this case when it is subjected to three-dimensional state of the stress. So first, in applying any yield criteria, the resistance of a material is actually given by the yield strength, and that yield strength is actually measured from the uniaxial tensile test. But in case of fracture or criteria, the ultimate tensile strength is generally considered, and that data is also extracted from the uniaxial tensile test from a specific material. But failure criteria for isotopic materials can be represented in terms of the three principal stresses, and when it is equal to the yielding or fracture in case of uniaxial tensile test data, then we can set the criteria in that way, or specifically to decide this criteria we generally try to link between the three-dimensional stress state to one-dimensional cases. But here the functional form, when it is a function of three different principal stresses, that functional forms actually need to decide here that better represents the plastic behavior of the material in case of three-dimensional stress state. Now usually an effective stress, which is a single characteristic numerical value that represents the three-dimensional stress state, and if we consider that equivalent stress or effective stress is equal to the one-dimensional stress state, say example here is the sigma c, that is the whether it may be yielding or whether it may be the ultimate tensile strength, that is decided to set the failure criteria. And this one-dimensional stress state, whether yield stress or ultimate tensile strength, actually is considered as a material property. Now we will see how we can look into the three-dimensional stress state. We can evaluate the yielding or yield surface specifically for different types of materials. So if you see the figure, actually this figure here, the expression of the stress versus strain, typical diagram. But when we do actual stress versus strain diagram of a specific material in a uniaxial tensile testing machine, in this case we keep the constant other variables. For example, we keep the rate of deformation of the material as a constant, we keep temperature as a constant, then we evaluate the relation between stress and strain, and for this specific other constant parameters, we can decide the yield stress value, we can decide the ultimate tensile stress value, we can decide the fracture strain for a specific material, and that is very true in case of uniaxial loading. But actually when you try to do represents the biaxial stress state, for example one element is subjected to two different states, sigma 1 and sigma 2. In this case, how we can evaluate the stress strain diagram for this case? So one simple approach is that keeping other parameter, for example sigma 2 as a constant, and we can keep all other parameters, and then we can conduct this tensile test, and we can get the specific stress strain diagram, and from that we can evaluate the yield point. Similarly, if we change the sigma 2 value, then probably the stress strain diagram will be different. So keep on changing the other parameters, keeping one parameter fixed, so we can evaluate the different stress strain diagram, and maybe the yield point will be different. So in this case, it is represents on a plane that the curve represents the actually the different yield point on the axis of the two different stress, principal stress here, that is sigma 1 and sigma 2. But since this change, if you look into this figure also, here if you see that it is the curve actually stress strain behavior with respect to the sigma 1 and sigma 2 axis for a fixed value of the sigma 2 dot. That means it's a deviated component of the sigma 2. So that values we are getting one constant line. Similarly, if we change this constant value sigma 2 dot, we may get other range of the stress where the yield point starts, or yielding of the material starts. Now keeping on the variation of the in terms of like delta sigma 1, this is simply changing the value of successive different tests sigma 1, or changing the value successively for different tests, we can generate the several yield data point for the specific material. So finally, when you try to represent these things, it can become like a curve that actually represents the yield curve, or if it is a three-dimensional stress test, we can say the yield surface can be generated in this way when we are considering the several tests by changing the stress level. This different type of surface can be generated, and that we can say that this is the start of the yielding. But it is better to represent the start of the yielding point not as a single point. Probably it can vary over a range, because here the variation of the stress, two different stresses, we can conduct the test, but at the same time if we change the rate, so probably there is a small variation of the yield point happen. So it is better to represent the surface, not this thing, it may be scattered within the small range. That range is represented, so we can represent the small range, and if we try to fit one specific curve within that range, probably we can get that yield curve or yield surface when it is subjected to not one dimensional case, when it is subjected to like two-dimensional stress state, or it is subjected to three-dimensional stress state. But remember, all these cases we are representing that state of the stress, or maybe we can say the state of the yielding with respect to the principal stress axis. Now it is a point here that when we conduct the different tests by increasing either sigma 1 and sigma 2, then what may be the increment of the consecutive test. So that should be the sensitive to the experiments. So probably if we do this variation delta sigma 1 or delta sigma 2, and over the stress axis, it cannot be a very smooth curve, that it can be a very zigzag kind of pattern, but the variation depends on the what are the increment value delta sigma 1 or delta sigma 2 for the successive test we have considered. At the same time, presence of strain hardening also requires a new specimen for each type during the experiment. So every time, if we want to consider the strain hardening coefficient, strain hardening effect of the metal, we need to consider every time so another new specimen. So on this way, it may be required a huge number of experiments to decide the yield surface of a specific material. So the yield surface may not be the smooth. At the same time, most of the measurement of the yield surface are made with the radial path, so that zigzag path. But this is the actual pure experimental data, and it is obvious that if you want to predict the yield surface for a specific material, we need a lot of experiments, a lot of data, and cost also involved to conduct all these experiments. So if you think into other way, if you try to represent the yield surface in a mathematical form, so we can define some yield function, but in this case we can assume that yield surface is closed surface and it's a smooth surface. Then we can define the different functional form of the yield surface, and accordingly we can predict the different theory, following the different theory, the shape of the or size of the yield function for a specific material. Now the approach may be like that. So if we assume that the yield surface may not be in this zigzag, maybe it's a smooth curve, and it can be a closed curve. In this case, we can define the functional form of the yield surface like that. F is the functional form, and that F is a function of stress state, and we can consider the normal stress as well as shear stress component when you consider symmetric stress tensor. So there is a 6 component, and that is equal to some constant value K. This is the very general form of the form to define the yield function for a specific material. Now if it is isotropic material, so that means the same properties in all direction. So it is possible to write in terms of the principal stresses, so we can further reduce the functional form of the yield surface, not in terms of the exact the 6 components of the stress, rather we can represent in terms of the principal stress components. It will be more easier to represent this thing, and that principal stresses we know comes from that part, the cubic equation of the stress connected to the stress invariance. So here J1, J2, J3 are the stress invariance, and we can represent the equation is like that, where lambda 1, lambda 2 and lambda 3 are the root of this equation, and that actually represents the principal stresses. So it is more approachable to represent the yield function in terms of the principal stresses rather than the individual 6 components of the stress. Now that we have already derived, this is the 3 stress invariants in terms of the principal stresses, sigma 1, sigma 2 and sigma 3. Now for isotropic material, since the properties are equivalent or properties are same irrespective of the directions, then we can represent, instead of the stress state, actual stresses, we can represent either in terms of the principal stress or either in terms of the stress invariance, because indirectly the stress invariance having all the components of the stress state. For example, here the J1, J2, J3 can already represented in terms of the principal stress component. So both way we can represent the yield surface in case of isotropic material. Now we can further reduce the number of the dependency of this stress state or this functional form of sigma 1, sigma 2 or the all the stress invariants in that way, that if you consider the very high accuracy plastic deformation is pressure independent, so that is generally observed in case of solids under hydrostatic pressure actually do not deform plastically. So hydrostatic stressor do not contribute to the plastic deformation of the material. So in this case we can further reduce the stress component in terms of the deviatory stress component. So here sigma 1 dot, sigma 2 dot and sigma 3 dot, if you see that this is represented in terms of the deviatory component, and that sigma h is actually the hydrostatic stress component, and that is the simply 1/3 of summation of sigma 1, sigma 2 and sigma 3, the 3 principal stresses. Now to do that, now we can say that if the plastic deformation is independent of the hydrostatic stress state, then we can represent the functional form is in that way, that K equal to F of J2 dot and J3 dot. So these are the two stress deviatory stress invariant, but it is not a function of the first stress invariant J1, because the hydrostatic stress component if we consider here, then this J1 dot actually becomes 0, since the principal this hydrostatic stress component of 3 principal stresses summation is equal to 0. That means the first stress invariant equal to 0. So we can further reduce the functional form dependency. So it depends, now it depends only on the 2 stress invariants J2 dot and J3 dot, and that is also for the deviatory component. Now we can say that for isotropic pressure independent material, that K is represented like this, function of J2 dot and J3 dot, these 2 stress invariants. Now the plastic response of the materials is often observed to be nearly the same in tension and compression. That means if we consider there is no Boesinger effect, then mathematically we can say that if there is no Bausinger effect, that means yielding with respect to tensile or compressive is same, then in that case the sign convention is not important here. That means it should follow like that, J2 dot sigma ij equal to J2 dot minus sigma ij, because and J3 dot sigma ij equal to J3 dot minus sigma ij. So this mathematical expression actually significant or holds true when we consider that the yield point with respect to the tensile or compressive load same. That means there is no Bausinger effect. But if you look into the expression of the this stress invariant J2 dot J2 and J3, if we see that if you change the sign sigma 1, sigma 2 and sigma 3, so expression doesn't change for J2. But if we change the sign for sigma 1, sigma 2, sigma 3, this expression J3, in this case if we see that actually J3 the changes the sign. So we can say that this convention actually not satisfied for the J3 dot. That means what we can say that J3 dot actually not independent of the sign, it depends on the sign. If there is a change of the sign from tensile to compressive, for example if we consider tensile as a positive and compressive as a negative sign, so if we change it, but it is not satisfying in this case, so we can say that f should be must be the even function of J3 dot. Okay, so we can eliminate the Bausinger effect by ignoring J3 dot. Okay, so but here actually the J2 dot is satisfying by changing the sign, but J3 dot is not satisfying, so we can neglect this if we consider the material is having no Bausinger effect. So therefore we can further reduce the dependency of the functional form. Here it is the function of only the second stress invariant, so K is a function of only J2 dot if material is isotropic, pressure independent and there is no Bausinger effect. Now further we can derive the J2 dot stress invariant, it is like that, and we can find out in terms of the principal stresses 1/6 of this, that sigma 1 minus sigma 2 square plus sigma 1 minus sigma 3 square plus sigma 3 minus sigma 1 square. So this is the stress invariant. So maybe if we consider the 1/6, this is a factor included in the arbitrary constant term. So this is the actual functional form in terms of principal stresses or in terms of the actual stress state, that is in terms of sigma 1,1, sigma 1,2 or actual stress tensile. Now this expression, actually shape of the function, is well known von Mises yield function. So that is widely used in case of plasticity analysis or plastic behavior of the materials. Now this we can cross check these things, that by looking into the expression of von Mises yield function, that if we look into the principal stresses and each principal stresses, if we look into that expression, that each principal stresses actually enters in the functional form equivalently. That means it actually assumptions or the isotropic material behavior is actually following by this conclusion that all the principal stresses actually enters here equivalently. Second point is that pressure independent, adding a constant term to the principal stresses actually does not change the functional form. If we add the constant term with the principal stresses, this expression, it actually doesn't change the functional form. That means this expression, this functional form is independent of the pressure. No Bausinger effect. The sign of the stresses does not alter the functional form. If we change the sign sigma 1, sigma 2, sigma 3, then it doesn't alter the functional form also. It's the same functional form, we can retain it. That means no Bausinger effect is considered here. So this is the, so this equation actually is a very important equation to represent the yield surface of a material, and this is known as von Mises yield functional form. Now if you do the further analysis, so graphically represents the yield function here. We can draw the one axis OA. On this axis is basically making the equal angle with respect to sigma 1, sigma 2 and sigma 3, and on this axis actually represents the sigma 1 equal to sigma 2 equal to sigma 3. So with respect to that, if we draw this the surface that actually represents the yield surface in case of three-dimensional straight state, but three-dimensional straight state here, if x, y, z is the actual Cartesian coordinate system when the initial state state is defined, but here we are converting the state state in terms of the principal stress sigma 1, sigma 2 and sigma 3. So on this stress state, or on this stress axis sigma 1, sigma 2 and sigma 3, actually we are representing the yield surface here. Now from this three-dimensional straight state we can represent further in case of two-dimensional yielding. For plane stress plasticity problem, sigma 3 equal to 0, so that K can be represented like that, sigma 1 minus sigma 2 square plus sigma 1 square plus sigma 3 square. Now if this is the actually K equal to this expression, represents the functional form of the yield curve here. Now if we do the uniaxial tensile testing and if we try to put the conditions here, so uniaxial tensile testing, for example, if sigma 1 equal to sigma bar, so one principal stress equal to sigma bar and sigma 2, sigma 3 equal to 0 from the uniaxial tensile test, and putting this condition here, we can find out that sigma bar equal to root over K by 2. So that means uniaxial tensile stress in the yield point, if it is yield point is sigma bar, that is equal to root over of K by 2. So we can replace the K in terms of the yield value in case of uniaxial tensile test data, and then we get the functional form of accordingly. Similarly, suppose we have the data for the biaxial stress state, and for example sigma 1 equal to sigma 2 equal to sigma bar and sigma 3 equal to 0 in this case, but here we can find out sigma bar is actually root over of K by 2. Similarly, if we consider the pure shear test, from pure shear states in terms of principal stresses, the condition is sigma 1 equal to minus sigma 1 and sigma 3 equal to 0. If we put these values here, this expression, then we can find out the sigma bar equal to root over of K by 6. So depending upon the different test data, for example whether it is uniaxial tensile test data, whether it is biaxial tension or whether it is pure shear condition, all this, the K value actually deviates. So in different cases different K value exists. So according to the availability of the tensile test data or shear stress data, we can modulate the yield functional form by putting this value, because the sigma bar actually we can directly evaluate from the test data doing the actual test. Now how this varies actually, all this data, if you plot it on the axis sigma 1 and sigma 2, that two principal stress axis, then you see that this point actually represents the for biaxial root over of K by 2. Here also it is the uniaxial root over of K by 2, because uniaxial is along one axis, other sigma 2 was 0 here, so that point exists at this point along on the sigma 1 axis. Similarly, pure shear, it was the sigma 1 equal to minus sigma 1, so at this point we can put the root over K by 6. So all these constants values actually represent the form we can be plotted on an ellipse. So the major axis of the ellipse is basically sigma 1 equal to sigma 2, and we can plot these things, and the major to the minor axis ratio is basically root over of 2 by 3. But in this case, the hydrostatic state of the stress varies from point to point along the ellipse. So this curve actually represents the different constant value for the different test conditions. Now, if we represent that actually the constant K determines the size of the yield surface as opposed to the shape. The shape of the curve is fixed, but K actually decides the size. Now K can vary depending upon the different load conditions. So the shape is fixed by the equation, that is true, and which is equal to K constant. Now K actually physically represents the hardness. So harder material requires the larger stresses to undergo the fast plastic deformation, or if it is softer material, probably the K value should be the less. So depending upon the K value, the size of the yield surface or size of the yield surface or yield curve can also be decided. Now the point is that, so equivalent or effective stress is basically the characteristic values, was basically we represent the one single value which is entirely calculated from the three-dimensional stress sets. It may be in terms of the principal stresses, but here the effective stress refers to the yield surface of an isostate surface representing all the combination of the stress that represent the elastoplastic transition. So let us look into the for a tensile test that we have already discussed. These are the conditions. So K becomes twice sigma bar square. So von Mises yield function becomes like this. So sigma bar square equal to half of this. So this is the functional form in case of von Mises yield function, and the sigma bar actually represents the data for the uniaxial tensile test. So according to the value of the sigma bar, we can represent the different shape of the size of the curve. So shape, suppose this is the shape, but size can be increasing if sigma bars increases for the different material. For example, one case is the yielding starts at the values of the sigma 1 bar. So this the represents of the yield surface for the specific material. Another material, maybe the sigma bar is different. So this is the representation of the curve, and sigma 3, if it is sigma 3 bar, this is the representation of the curve. So basically here sigma 3 greater than sigma 2 greater than sigma 1. So accordingly, the depending upon the values of the yield point, we can represent the yield surface by simply changing the values of the K. Now, if it is pure shear test, for example, we have the value, or we can conduct the test in case of pure shear conditions. So for pure shear condition, these are the relation between the K and the shear stress value. Then the representation of the yield surface in case of pure shear is, this is the functional form, which is different for the actual tensile test data. So that is the variation of the yield shape and size of the yield function according to the type of test or according to the data available, whether it is shear test data or whether it is having the tensile test data. Now graphically how we can represent this stress state, let us look into that, what we have discussed in the beforehand, that O is the axis that represents the sigma 1 equal to sigma 2 equal to sigma 3, and it is on the principal stress axis system, sigma 1, sigma 2 and sigma 3. So D is actually state of the stress, that is sigma 1, sigma 2 and sigma 3, and C point actually represents the average stress value. Okay, so that average stress value, or maybe we can say the hydrostatic stress component here. that is the 1/3 of sigma 1 plus sigma 2 plus sigma 3. So basically OC represents the pure hydrostatic state of the stress in this case, and CD will attain some critical value because D point is actually represent the actual stress, principal stress value sigma 1, sigma 2 and sigma 3. So that actually represents the actual state of the stress in terms of the principal stresses sigma 1, sigma 2 and sigma 3. Now CD can be represented that OD minus OC, so in the vector form. Then CD can be calculated like that because according to the coordinate system, so OC actually represents that this sigma average value sigma 1 plus sigma 2 plus sigma 3 by 3, and from there you know the coordinates C and D, so CD can be represented this way, sigma 1 minus sigma average square plus sigma 2 minus sigma average square, so like this. Now CD can be square can be represented this thing sigma 1 sigma 2 equal to, and maybe it can be represented some fraction x is the some numerical value into k. So here CD is the actually some critical value. So okay, OD is actually represent the actual stress state, that is consist of the OC plus CD. Now looking into these things, we can find out, we can predict the yield criteria like that. F is a function of sigma ij and k, that is the yield criteria, but k not only decides the yield point here, but at the same time we can take care of the strain hardening effect in case of plastic deformation of the material. Now we'll see how we can look into that part. Now if we try to, after identification of the yield point of a specific material, that means it is when it is just cross the elastic limit, then with the further deformation of the material it goes to the plastic stage, and there is an increment of the stress value possibly due to the strain hardening mechanism. So in this case we can predict further the stress state in the plastic zone also if we consider the effect of the strain hardening. But normally we consider the increment of the stress state with respect to the increment of the stress part. So actually this whole analysis is based on the how we can increase, how we can update the stress state considering the effect of the increment of the strain value in the plastic deformation zone. For example, because of that we need to predict the flow rules and the normality conditions. So flow rules in the sense that during the plastic deformation zone, how we can sustain the plastic deformation, and that can be better represented in terms of the flow of the material during the plastic deformation. So during yielding, the ratio of the resulting strain depends on the stresses that causes the yielding. The general relation between the plastic strain and the stress states are called flow rules, or are decided as a flow rules. For example, suppose this is the yield curve on the stress axis sigma 1 and sigma 2, and on this yield curve, with the further straining, with the further deformation of the material, what may be the increment of the plastic strain. Now increment of the plastic strain is actually proportional to the, if we define some functional form of the yield curve, or if we define the functional form of the yield surface, so that partial derivative of the yield function with respect to the stress state and proportional, and that proportionality constant we can consider the d lambda. So basically d lambda is a constant value here, constant term here, and that d lambda actually sometimes the deciding factor, what is the values of the increment of the plastic strain amount. So it is a combined effect of the increment of the strain, actually depends on the what are the yield function we have defined. So what is the nature of the yield function, or maybe what is the mathematical form of the yield function, and what is the stress state, and some constant term that constitute the amount of the increment of the plastic deformation or plastic strain during the yielding of a material. Now this law states that the flow will actually decided by the few factors here. The direction of the strain increment, actually d epsilon, is independent of the d epsilon. So the increment of the strain and increment of the stress, actually they are independent with each other direction. And this curve, of course, it represents the one yield function. Suppose f equal to, f is the functional form shape and equal to k. This is the shape of the, that f decide the shape and k decide the size of this yield surface. Now d epsilon is a vector we consider as a normal to the yield surface. So we define the direction of the increment of this d epsilon is basically normal to the yield surface, and d lambda is a arbitrary constant. So this is sometimes called the normality constant in case of plastic deformation of a specific material. So when you define this incremental mode of the plastic deformation as a function of this constant and the functional form of the yield surface, then we can further reduce, or we can further deduce the, assuming the bond meshes yield function, then we can further manipulate the different information here, the increment of the strain ratio here. For example, this we consider the yield function. So f equal to k, and that sigma bar is defined basically in case of the uniaxial tensile. Now if you do these things and if you try to evaluate the d epsilon 1, so either we can evaluate d epsilon ij, or in terms of the principal strain component also d epsilon 1, 2 and 3, all these three components in terms of. So d epsilon 1 equal to, put this formula here, and dou sigma by dou sigma 1 principal stress, and okay. So I think it will be the f functional form here, and if you do the derivation, you can find out this expression, and finally you will be getting this expression. So increment of the strain in terms of the principal stress value and the constant term d lambda. Similarly d epsilon 2 and d epsilon 3. So this we can find out the ratio of the increment of the strain component d epsilon 1, d epsilon 2 and d epsilon 3 from this normality conditions. But at the same time, it to be noted that all this plastic deformation, we need to assume that the material volume remains unchanged. That means d epsilon 1 plus d epsilon 2 plus d epsilon 3 equal to 0. Now we can do further analysis on this thing. For example, for uniaxial tensile test in x1 direction, that sigma 1 equal to sigma, sigma 2, sigma 3 equal to 0. So we can find out this increment of the strain epsilon 1, epsilon 2 and epsilon 3, and further the ratio can be evaluated like this. Similarly, for biaxial tension, we can put this condition and we can find out this ratio, and from there we can find out all this ratio. Even for plane strain also, d epsilon 1 equal to d epsilon and d epsilon 2 equal to 0. If we put it, and we can find out the stress ratio here, 1 is to 1 by 2 is to 0, or 2 is to 1 is to 0, like that. Now similarly, like equivalent stress, or we can find out the effective or equivalent strain component also. So direction of the strain is determined by the yield functional form. That increment of the strain path is always normal to the yield function. The size of the strain increment is related to increment of the stress value and the flow curve. It depends on these two things. But multi-axial strain increment can be represented to an equivalent increment in a uniaxial tensile stress based on the equivalent plastic work. So like the equivalent stress, which represents actually the stress state in terms of all the principal stresses, and that equivalent stresses, the one single value, consist of the all the stress state here. Similarly, we can represent the increment of the equivalent strain, which consists of the increment of the strain in case of multi-axial direction. So in that case, maybe that amount of the equivalent strain can be evaluated from the uniaxial tensile test data and from the amount of the equivalent plastic work. So if we see, so sigma bar, if we say this is the equivalent stress and df, this is the increment of the stress, so that this stress and the increment of the strain, that actually equal to the amount of the work done due to the increment of this strain value. So amount of the work done per unit volume is represented like this. So these two cases, the single value, one is the stress, another is the incremental strain. That represents in the actual stress state and incremental of the stress state. So or sigma I by d epsilon j, that means in terms of the principal components. So we can represent that sigma 1 d epsilon 1 plus sigma 2 d epsilon 2 plus sigma 3 and d epsilon 3. This is the equivalent plastic work method, and from here we can find out the correlation like that. So this d epsilon bar equal to sigma ij by sigma bar into d epsilon ij. So that we can further use the normality condition here also to bring that constant term. So these are the typical representation of this thing. Now most of the time increment of the equivalent increment of the strain is needed in terms of the d epsilon ij, so actual strain component, of course in the incremental form, so that total equivalent strain can be evaluated directly from the geometric strain path. Second point is that we need to obtain the sigma ij as a function of incremental strain path. That cannot be obtained explicitly, so numerical treatment is also required. So in this case we need to define the yield function. So let us see how we can graphically represent this strain hardening effect here. So if we look into that from A dot to B dot with the increment of the strain amount delta epsilon. So in this case it is obvious that from the graphical representation of the stress strain that there is an increment of the stress. So mathematical condition is that delta f functional form. So delta f basically represents the functional form of the yield surface, and delta epsilon. So multiplication of these things should be greater than 0. Then that represents actually strain hardening of the material. So strain hardening, as simply we understand that increment of the stress level from A dot to B dot with the deformation, with the further straining of the material. Similarly, if we consider from A triple dot to B triple dot here, A double dot to B double dot here, so here the strength level actually decreases. So that is called actually strain softening here. So the mathematical representation of this thing should be delta f, and delta f should be less than 0. Similarly, at A triple this point actually there is no increment of the strain, so no strain hardening is happening at that point. So basically the incremental form is equal to 0. So probably we can say this is the optimum point here where there is no strain hardening. So up to that A3 dot point there is an increment of the strain due to strain hardening, and after that there is a decrement of the strain due to the strain softening. Now effective strain, or maybe better to say the incremental strain, that can be derived further assuming the von Mises yield functional form. for example, this is the plastic normality condition, so that represents the increment of the plastic strain, but we need to define the different parameters here, the arbitrary constant d lambda, and we need to define the functional form of f, yield functional form. And suppose here we using the one message yield function in tensile, this is the functional form, and now we can find out that from the equivalent plastic work done, that we have already derived the d epsilon bar in terms of the sigma 1 d epsilon 1 here. Now this is also we have already discussed that d epsilon 1 equal to in terms of principal stresses and the plastic multiplier probably d lambda, that constant term. Now with the manipulation we can find out this, and also we use this relation, the material volume point of view, d epsilon 1 plus d epsilon 2 plus d epsilon 3 equal to 0 when the conservation of material volume is maintained here. Now equivalent strain here in terms of the principal stresses and strain component, we can do the manipulation here, putting all this value. If we put it, finally we can getting this value. Now incremental strain in terms of stress component, it is there. Now if we do these things, we are getting this expression that is equal to the 2 sigma bar square, and that comes from the one basis yield functional form for the tensile test. And then from this relation we can find out d lambda equal to in terms of this, and finally we will be able to find out d epsilon bar equal to 2/3 of d epsilon 1 square plus d epsilon 2 square plus d epsilon 3 square root of that. So this is the amount of the equivalent strain in a incremental form in terms of the individual component d epsilon 1, d epsilon 2 and d epsilon 3. Of course this expression is valid if we assume the one misses yield functional form in case of uniaxial testing, tensile testing. Now this expression is more practically representation of the equivalent form is more practically valid if the individual component max less than equal to d epsilon I max, or 1.5 times of the epsilon equal to max. So this is just practical guidelines, the accuracy of this form of the equivalent strain in this case. Of course with the further manipulation it is possible to express this the equivalent form in terms of the actual component 1 1 2 2 3 3 1 2 2 3 3 3 if we know all the geometric strain path and all the shear component, shear strain and the normal strain component, then we can further represent this way. Similarly, in terms of the strain rate, we can represent the effective strain rate during the deformation in terms of all the strain rate component like this. And of course, all this expression definitely we are following the von Mises yield functional form. Now we come to that point, strain hardening, or basically we can say the plasticity with the strain hardening. If we see that von Mises yield function has not explicitly mentioned of strain hardening or how the yield surface evolve during the application of the load or during the plastic deformation stage, that explicitly not told by the von Mises yield functional form. That this von Mises yield functional form is just represents the shape of the curve. We can modulate it, we can reshape it according to the different test condition. Now if we consider the effect of the strain hardening, maybe we can see that how this functional form actually evolve. First case is the isotopic hardening. The more general case we often use this thing. The only single parameter sigma bar is necessary to describe the yield surface. Maybe this is the, if you look into graphically, this is the one functional form F1, but the constant term K1 or sigma bar is cases. Now if the sigma bar actually changes to sigma bar 1 for example, the shape remains, the functional form change from F1 to F3. Actually functional forms remains the same, only there is a change of the constant term. So that evolution from one stage to another stage can be represented like that in inertial tensile test from here to here. So that means from this point to that point, this point to that point is basically increment of the strain value due to the effect of the strain hardening. Similarly, in case of kinematic hardening, the yield surface size and shape actually remains the same, but the location translates according to the current stress vector. If you see graphically, the shape and size remains the same, but the center point actually translates according to the new stress state. So this is interesting in case of the when there is a Bausinger effect is important to consider, or that is the abrupt reversal of the strain path. If we consider, in this case maybe kinematic hardening model is the more appropriate, but some certain material behavior, if we want in such a way that the material behavior can be represents the both the models of the combined isotropic and kinematic hardening rule. Now if we look into the flow rule, the initial yield surface may expand uniformly or translate rigidly to the current stress state point by each respective rule. So once we discuss that flow rule, always we try to represent in such a way that deformation of the material or flow of the material happens from during the plastic stress from one point to the another point. So there are several flow rules exist. One case is von Mises functions. We represent simply that F equal to J2 dot is basically the second invariant, Dimitrov invariant. It represents the von Mises functional form, yield functional form. Is often used within the simpler rule of isotropic hardening, and it also leads to the flow rule of the Lévy-Mises. In this case, the functional form E, or maybe we can say the yield surface, is represented in terms of this stress component, strain component, and another is the hardening parameter. That hardening parameter we can find out make is the equivalent form of the plastic work done. So this is the simple functional form increment of the dF in terms of the all the variable here, where dou epsilon IP plastic and dx actually depends on the direction of the incremental stress vector d sigma ij from a point P and F equal to 0. So that means F equal to 0 on that point, and from a specific point, what is the direction of the stress vector, incremental stress vector? The x, or basically hardening parameters, depends on that. Here if we see that this is the expression of the one yield surface for a specific condition, and at a point P, if you see that for a glass to plastic loading, that functional from dF keeping sigma as a constant, in this case this is the expression of these things, del F by dou sigma ij d sigma ij. So in this case dF sigma is greater than 0, one condition, so that increment of the plastic strain positive greater than 0, and hardening also. So there is a hardening parameter, so dx, so change of the hardening parameter is basically equal to greater than 0. So this condition is represented like that. So this side, so this is the one specific functional form, so this side increment of the strain, and this along this direction, this is the d sigma j and making some angle phi. So this represents the loading condition, and that is the glass to plastic loading condition. Now when plastic unloading happens, so that means plastic recovery happens from the plastic region, then that is the representation is that dx functional form is basically the inward direction. So that is less than 0, and increment of the plastic strain and increment of the hardening parameter is considered as a 0. So this is the physical representation of that. A neutral loading is basically refers to a change of the stress state along the yield surface, but increment of the functional d f equal to 0, d epsilon also 0, and hardening parameter also 0. So that path actually represents the neutral loading. There is no hardening effect, or loading refers to change of the stresses along the yield surface. Okay, so these are the typical representation of the different loading, unloading condition when you try to consider these things in a plasticity model to analyze the plastic deformation of the material. Now sometimes we define the plastic potential function for a plastic loading condition. The potential function describes actually closed convex surface in a strained space whose outward normal defines the direction of the plastic strain increment vector. In this case, the normality condition is defined like this, which is same as what we discussed earlier, the normality condition during the plastic deformation, but the functional form may be different here. Now sometimes we use the flow rule is then associated with the yield function, so it is better to describe always or decide the flow rules during the plastic deformation of the material that is associated with the yield functional form. So that is the normality condition that we are defining, and here we see that isotropic hardening, how we can represent these things. So isotropic hardening means on the strain, principal strain axis, that represents the maybe first circle or the first functional form represents the corresponding to the yield point of the just cross the elastic limit. Then the strain level actually increases with the further deformation, or that is because of the strain hardening. So if it is corresponding to this yield point for the material, this point, and when we consider strain hardening increment of the stress, so yield surface actually evolves this way in case of isotropic hardening. This is the graphical representation. This is the second point. Then when the yield point or strength level actually increases from first yield point to the second, so that actually evolves the yield surface or change of the shape, change of the size actually depending upon the hardening effect for this specific material. So this is the representation of this thing. Now yield surface depends solely upon of the increment of the stress, while its size actually depends upon the hardening functional form of the hardening parameter. So if x is monotonically increasing hardening function of a suitable scalar quantity psi of the plastic strain or plastic work, that can be evaluated from the amount of the plastic work done in this case. So change in F will now depend upon the whether df greater than 0 or df equal to dx, all these three different conditions: elastoplastic loading, elastic unloading, and for neutral loading, that we have already discussed this thing. Now no further hardening can occur as the material is either unloaded or is subjected to the neutral loading. So basically here we are not considering any hardening effect when there is an unloading conditions or whether there is a neutral loading. That is the important. So now when plastic strain is large and elastic part is actually very less or small enough to be ignored, then we generally consider the Lévi-Mises theory to estimate the total deformation in a elastoplastic solid. But when we consider the elastic and plastic stress component are comparable in their magnitudes, then Lévi-Mises equation may not be acceptable. In this case, Prandtl-Ross flow theory is more applicable. Now we try to get the overview of this different kind of Lévi-Mises flow theory or Prandtl-Ross flow theory. First we consider that if f is a function of the second invariant that we have used and the deviatory stress component to derive the one Mises yield functional form, and assuming that hydrostatic stress does not contribute to the plastic deformation, that was true, and no Bausinger effect was there. Now this f sigma ij, this should not be considered here, is a function of the psi, which is the isotropic hardening. So in that say this yield function is basically a equivalent to the second invariant of the stress invariant. So that we can write this way, or this is the expression. Now size the equivalent plastic work done, we can find out from the equivalent plastic work done, and yield surface can be evaluated in terms of the diametric stress component here. So there is a several way to define the hardening function also. So sigma bar as a function of the hardening, but this is the simple equivalent form. So basically we can find out this hardening parameter or hardening function looking into the equal amount of the plastic work done. That hardening function can also be established from the tension test, or alternatively can be established from the plastic work done hypothesis also. Now Levi-Mises theory, we can look into this further expression whether the hardening parameter functional form can be represent the sigma bar square by 3, and where we can find out the sigma bar as a function of H or F, like that. So Levy and von Mises consider the incremental theory of plasticity when isotropic hardening is combined with the flow rule. But here the association of the plastic potential function with the von Mises potential function. So basically the plastic potential function is here considered as the von Mises yield function in this case. Now this von Mises yield function, the functional form can be the in terms of the diametric stress component and of course second stress invariant, and we see that actually the increment of the plastic strain component is proportional to the diametric stress. We can use this relation. So we can finally find out that this is diametric stress component is the index form. We can write it in this way. Now d lambda is the scalar factor of proportionality, and that linking to the current equivalent stress to an incremental equivalent of the plastic strain, and where the coordinates on the curve is basically sigma bar and the d epsilon bar of a uniaxial flow curve. So that is link can be uniaxial flow curve. We can use in the as a coordinate sigma bar and d epsilon bar. Now if you mean stress, here is the 1/3 of sigma bar, and this is the deviatory component for the one for uniaxial case, and we can find out d lambda equal to this. So here we can see that d lambda is inversely proportional to the incremental plastic modulus. So d lambda can be evaluated actually if we evaluate the consider the equivalent or effective stress value or equivalent or effective incremental of the strain, and accordingly we can decide the this d lambda value in this case. Now for nonlinear hardening from the strain and work hardening hypothesis, we can find out the functional form H and F in terms of this equivalent stress and equivalent work done. But all this can be derived if we consider the Ludwig's power law, and this is the expression, and we can find out from this expression we can find out the d lambda in this case, or we can find out simply okay, in this case we are trying to find out the d lambda here from the Ludwig's power law. So for a triaxial stress system, the principal plastic strain increments can be represented in terms of the principal stresses or equivalent amount of the incremental plastic strain, and that is corresponds to the following the Levi-Mises flow theory. Now Pandel-Russ theory telling that total incremental strain theory sums that both the part is there, elastic and plastic incremental part is there, so that we can total incremental of the strain consists of the not only on the plastic part, there is elastic part and there is a plastic part as well. So in this case we can represent, this is the with the manipulation we can represent these things. So one first part represents the plastic part and second represents the elastic part. Of course this theory is basically applicable when we try to capture the elastic recovery during the plastic deformation. That means both elastic and plastic component we are considering. Now the expanded form of the equation can be represented like this, similar this is the plastic part and the elastic part, and this is the shear component. So shear component consists only of the in terms of the one single component is there. Now, if we consider the elastic analysis, these are the simple expression for the stress strain relation within the elastic limit, and all the normal stress component, normal strain, and shear strain, shear stress component. So we represent this component in terms of this expression stress, I think in terms of the column vector. D matrix is called elasticity or stress strain matrix, and epsilon is the strain components here, or the strain column vector. Now, according to the Pendel's flow rule, the plastic increment of the strain is actually proportional to the deviatory component, and we can define this d epsilon, and that deviatory component can be represented as epsilon for d rho f by d sigma, and that actually comes from the normality condition. So while f is defined actually yield function. So basically this is the total strain consists of the incremental elastic strain and incremental plastic strain, and then we can represent the stress in terms of DEP matrix and with the incremental strain. So finally we can say that D inverse D epsilon, that is corresponding to the elastic part, and this is the plastic part. Now d lambda can be calculated from the plastic work done and the results from the uniaxial stress strain curve. So we can use all these relations here to find out that d lambda from the, so d lambda actually here you can find out by looking into the uniaxial stress strain diagram, and putting that value we can do the further analysis. So that was the way we can do the plasticity model when we are considering during the deformation, when both the elastic component as well as the plastic component are there, by following the Prandtl-Gross flow theory. So according to the practical application of the material, we can use the Lévy-Mises flow theory during the plasticity analysis, or we can use the Prandtl-Gross flow theory. So this was just an overview how we can use this flow theory in the plasticity model. Now we come to that point, plastic anisotropic cases. Here, preferred orientation of the grains or crystallographic structure actually introduce the anisotropic plasticity within the material itself. Sometimes mechanical fibering, that means alignment or elongation of microstructural features such as inclusion and grain boundaries, actually introduces the anisotropic condition in case of during the plastic deformation. So general equation, that is the Hill quadratic equation, is represented that this way. So there are here all the in terms of the actual stress components in case of Cartesian coordinate system x, y, z. So all the normal stress and the shear component are there, and by introducing the different constant term F, G, H, L, M, N, it is possible to bring the anisotropic behavior by simply using the quadratic equation. Now, with further simplification, that if the principal stresses coincide with the x, y, z axis, and if there is planar isotropy, the above equation can be simplified to this equation. Of course, this equation is basically following the von Mises yield functional form. Here, this von Mises yield functional form, by introducing the one constant of R, we can bring the planar anisotropic condition during the deformation of the material. So here, if is H by G, H by F is basically we have defined as a constant term R. And for a uniaxial tensile test condition, sigma 1 equal to sigma bar, sigma 2, sigma 3 equal to 0, we can find out. And of course, for plane stress condition, sigma 3 equal to 0, we can further modify this equation. For example, in this case, for plane stress condition, this is the equation of the anisotropic condition, or anisotropic yielding. Now here the anisotropy is actually introduced in the sigma x and sigma y, or I can say the sigma 1 and sigma 2, by introducing that constant term r. And if you see that there is, with the change of the r value, simply if r equal to 1, r equal to 1 is the simple represents the in two-dimensional von Mises Ill functional form in case of tensile test. But if r equal to if we vary the different r value, so if r equal to 0, then it becomes a circle, equation of a circle. And accordingly, if we vary the r equal to 1, 2, 3, 4 and r equal to 5, then we can see there is the deformation actually happens one specific direction. So that direction is the basic represents the anisotropic behavior of the material, and this represents the curve. This curve actually represents on the 2D, two-dimensional case, that represents the effect of the anisotropy simply by changing the values of the r, and we can represent the yield functional form at different values of the r. Now this is called actually Hill's 1948 yield criteria for planar isotropy. Now we can further analyze in terms of the r. We can do these things. So we can define the beta is the ratio of d epsilon 2 by d epsilon 1 for sigma 3 equal to 0, that means plane stress condition, and alpha equal to ratio of the sigma 2 by sigma 1 for sigma 3 equal to 0. And then we can derive this formula beta equal to in terms of r or in terms of alpha. So if sigma 3 equal to 0, then we can find out the sigma bar by sigma 1 in terms of alpha and r. And finally we can represent the d epsilon bar equal to d epsilon 1 by sigma 1 by sigma bar 1 plus alpha beta. So but in this case, sometimes the Hill criteria often overestimates the effect of the r value. Now if by changing the exponent, we can represent the general form of the equation. Consider the anisotropic behavior in terms of the changing the exponent a. A is generally considered the even exponent and which is higher than 2. For example, a equal to 6 for BCC material and for a equal to 8 for the FCC material. So that functional form can be further modified this in general way by introducing the F, G, H, 3 different constant to bring the anisotropic behavior of the three-dimensional state, and the a, the exponent, is the different in all the cases. Now this was all about the theory of the plasticity. I have tried to cover the very basic idea that what we generally used during the analysis of the plasticity, not much going into the in-depth analysis of the different theory and their mathematical derivation, but looking into the knowledge of a theory, we will try to focus on the some numerical problem which can be covered here. For example, first example, if we consider the strain path AB shown in the figure. Each path begins at epsilon 1 equal to epsilon 2 equal to 0 and ends at epsilon 1 equal to 4, epsilon 2 equal to 3. Find the effective strain for each path using the following yield function. So this problem is like that. This is the 0, 0 point, and we define two paths. A path, actually it comes directly at this point. Another path is B path, is from here to come this point. So in these two paths, we need to find out what is the effective strain, assuming that there is a von Mises yield function, or assuming the normal quadratic there is a R. So to do that, first we need to find out the correlation between epsilon 1 and epsilon 2. So if we look into the path A, epsilon 2 is represent the straight line, epsilon 2 equal to m epsilon 1. Okay, so m, the gradient basically can be obtained from the geometric point, because this is 0, 0 coordinate and this is 4, 4 and 4, 3 coordinate. So accordingly geometric coordinate we can find out the slope. and from here we can find out the relation between the epsilon 1 and epsilon 2, and we can use this doing the derivative, we can find this relation. Now from here, but another point is that material volume remains constant, so we can use this relation, and d epsilon 3 in terms of the d epsilon 1. Now the effective strain in the incremental form we have already derived, and this is again, it is valid if we consider the yield function as a von Mises functional form. Then if we find out, then we are getting this relation between the effective strain and this d epsilon 1. Now if we look into that, d epsilon 1 actually varies from the 0 to 4. 0 to 4. So if we put the integration limit from 0 to 4, we can find out the absolute value of the incremental effective strain for the path A. Now similarly for the path B, we can similar analysis we can conduct here. First, but path B consists of the two parts, two linear path, this and another one is this. So basically 1 0 to B, another is the B to A. So that path, so we can follow the similar analogy here, and this is the path O to B, and second part is the path B to A. So we can get two components here, and we do the individual integration here if we find out this thing. Okay, so remember, or maybe noted here, that from path B to A, the integration limit actually from 4 to 3, so there is a decrement. So second component is actually negative component here. So finally effective increment of the strain is this one. So by following the normals Hill's quadratic equation, we can derive the effective strain in the similar way. Now if we look into the another example, that strain measured on the surface of a piece of sheet metal after deformation are. So these strains are measured after deformation. The stress strain curve is represented, approximated by this one, assuming the von Mises criteria, and assume that the loading was such that epsilon 2 by epsilon 1 actually was constant. Calculate the levels of sigma 1, sigma 2 reaches before the unloading. So from here we can find out the equivalent strain here. Now if the straining is proportional, so epsilon 2 and epsilon throughout the deformation, then we can say that ratio exists so that total effective strain can be represented as a single form rather than incremental form here. Now from the constant material volume we can use this one or this one. Then we can find out the relation, the epsilon 1 and epsilon 2 are given here. So we can find out the epsilon 3. From here we can find out what is the effective stress value in this case. Now we check whether this effective stress values in between the guidelines or not. So if we see that maximum is 0.12 and 15% of the maximum is the values of the effective strain. So it lies in between that. Basically we are following this guideline. So we can consider the calculation of the effective stress here. Now effective stress sigma bar equal to the stress strain relation here is given, but that when the stress strain relation is given here, so we need to consider the what is the effective stress value and what is the effective strain here. Then we can find out the effective stress value equal to this one. Now for the plane stress, the effective stress can be written this thing in terms of the alpha, where sigma 2 by sigma 1 ratio is defined by alpha here. Then we can find out, so the ratio according to the flow rule, we have sigma 2 equal to 0 here, and we can find out the ratio is beta in terms of alpha or alpha in terms of beta. That alpha and beta is already defined. Then we can find out alpha and because beta in terms of alpha, because alpha we have beta is given, so beta is given because this is actually epsilon 2 by epsilon 1, the epsilon ratio of the epsilon 2 epsilon 1 are given in the problem. Now from here we can find out the alpha, and using this relation we can find out the sigma 1 here, and we can find out the sigma 2. So this is the range sigma 1 and sigma 2 can be raised if we, according to this definition of this problem. Now similarly, if we given the R values is given in all directions, stress in the biaxial tension with sigma z equal to 0. So measurement indicates that throughout the deformation epsilon y equal to 0. So we need to find out the stress ratio alpha sigma 2 by sigma 1 according to the quadratic yield criteria and non-quadratic yield criteria with a equal to 8. So this is a typical expression of the alpha, but here it is given that beta equal to 0. So we can find out the alpha here. And similarly, when there is a non-quadratic yield criteria, we can use a as a 8. We use this relation for the similar analogy what we are following in case of the quadratic function itself. But in this case, we need to evaluate the alpha in terms of trial and error method. So by solving this equation by trial and method, we can find out alpha equal to 0.52. Now we look into the next final problem here, that find the ratio of the principal stresses sigma y equal to sigma x by 4, sigma z equal to 0. Assume the von Mises criterion. So straightforward, assuming the von Mises criterion, we can use the ratio between the incremental strain component is the in terms of the principal stresses is like this. Here you see here sigma y is basically represent the principal stress sigma 1 and sigma s is principal stress sigma y is principal stress sigma 2, sigma x is the principal stress sigma 1 and sigma z is the principal stress sigma 3 equal to 0 here. And if we put it here, the ratio is like that. Basically we have used this relation that we have already discussed in the theory. So with this I can conclude this section basically, which is related to the three-dimensional state of plasticity model. So in this section we have discussed the how we can evaluate the strain yield surface assuming the von Mises yield criteria, and how we can put the normality condition and how we can find out the effective stress or effective strain when there is a existence of the three-dimensional plastic stress strain, and different manipulation of this thing to find out the different constant term which is related to the incremental plastic deformation, and that constant term can also be evaluated from the amount of the plastic work done principle. So in this case I have tried to represent all the plasticity or plastic deformation of the material in a short period of time and in a very simplified way and with the certain example. Hope it will be helpful to make some understanding of the plastic deformation of the material. Thank you very much for your kind attention.